Hi everyone, welcome to this video lecture on K nearest neighbor. So for the purpose of this video lecture, we're going to discuss in detail what the technique behind KNN is and what are some of the possible applications of the KNN algorithm. So KNN is the short form which we generally use to refer to this algorithm, and it stands for K nearest neighbor, where K represents the general form of the numbers of neighbors that you want to consider in order to either classify a new data observation or to use it in order to replace missing values in your existing data set. So I'd like to start this video lecture by quoting some of the famous sayings that motivational speakers refer to. And you might have heard these yourself, that you're the average of the 5 people that you spend the most time with, or show me your friends and I'll show you your future. So basically, KNN is an algorithm that uses the same ideology to help you either classify an unknown data observation or to help you replace the missing values of the data records that you have in your data set. So KNN, like I said, can be either used to classify a categorical outcome, or it can help you to estimate the values of a missing continuous outcome. In the KNN approach, the predicted outcome for an observation is based on the K most similar observations from the training set, and there are different measures of similarity with respect to the input variables that you have in your data set. So let's say, for example, you're trying to identify if a new customer is going to default on their loan payment or not. That is a categorical outcome. And you can use certain features about the customer that you already know to help you decide on the value of the categorical outcome, loan default. There are different measures of similarity that you can use within the KNN algorithm to help identify the neighbors to the data value that you're trying to classify. Different statistical softwares use different types or different measures of distance, but the most commonly used measure of distance is the Euclidean distance, and that's the distance that we will use in our demonstration of the KNN method. So the Euclidean distance, the reason why it's most popular and most commonly used is that you can calculate the Euclidean distance for multiple input features or input variables to help you identify what are the nearest neighbors to the unknown data outcome. There are other types of distance that can be used within the KNN method. This include the Minkowski distance measures. Euclidean distance is actually a part of the Minkowski distance measures family. The Manhattan distance is a common one too. Chebyshev distance, Lorentzian distance, Canberra distance, Jacquard distance, or the squared chord distance measures. So all of these are different types of distance measures that you can use within the KNN methodology, depending on which distance measure suits your data set the best. Because the most popular one is the Euclidean distance measure, that's the one that we're going to use in our demo lecture today. And the formula for the Euclidean distance measure is that if you're using two input variables, x and y, then you would have to calculate the distance between x and y, square up the difference, and then add it across all the different observations to get the square root, which would represent a measure of distance of this new data observation compared to the other data observations in your data set. This is going to make a lot more sense once we do an example with this in an Excel file just shortly. But the basics of the KNN algorithm is that you compute the distance and then you choose the K samples in the sample distance and identify the nearest one to your unknown sample little d. Once you've identified the nearest neighbors to D, you can assign a class to D based on the most frequent classes or the majority class. A critical aspect of effectively applying the KNN method is the selection of the appropriate features on which you want to base the similarity. So for example, when computing similarity with respect to too many features, the Euclidean distance is less discriminating of a measure as all the observations become nearly equidistant from each other. There is no automated feature selection that exists within the KNN method. The preliminary data exploration paired with experimentation can help us identify the most promising features that we can include in our analysis. For this video lecture, I'm going to explain the steps to classify categorical outcomes with the help of the k-nearest neighbor algorithm, and we'll do another example that will help us estimate continuous outcomes with k-nearest neighbors algorithm. When you're trying to classify categorical outcomes with the k-nearest neighbor algorithm, you're going to directly use the entire training set to classify observations in the validation and the test sets. So when KNN is used as a classification method, a new observation can be classified either as class 1 or class 0 depending on its nearest neighbors that you identify and what their values are. So typically you would have to select a cutoff value. Generally the cutoff value is 0.5, so a distance measure which is above 0.5 would be assigned to the class 1 class, and if it's below 0.5 it would be assigned to the class 0 class. The value of the k is something that you need to decide for your analysis. So k can range from 1 to n being the full sample size in your training set. So if k is equals to 1, then the classification of a new observation can be set to be equal to the class of the single most similar observation from the training set. On the other extreme, if k is equals to n, then the new observations class is naively assigned to the most common class in the training set. Generally, smaller values of k are more susceptible to noise in the training set. So if you feel like there's a lot of noise in your training set, it's advisable to increase the value of k. On the other hand, larger values of k may fail to capture the relationship between the features and the output class because you're simply using the average or the majority class to help you classify this unknown or new observation. Note that using the different values of k, you have to select a value of k, let's call that k star, which would be the best value of k, best in terms of the smallest classification error on the validation set. So you might have to rerun the algorithm multiple times with different values of k so that you can identify the most optimal value of k, which gives you the smallest classification error, or which helps you predict the class of your new data observation most accurately. The actual value of k that you're going to use for your final analysis would obviously depend on the classification error or the prediction error on your validation set, but typically values of k ranging from 1 all the way to the square root of n divided by 2 are typically considered. So let's say, for example, you have a sample size of 16 observations. Then a good value of k to start the algorithm with would be the square root of 16, which comes out to 4 divided by 2. So k is equals to 2 might be a good starting point. If your data is smaller, it doesn't hurt to run the algorithm multiple times with different values of k and see which one gives you the smallest classification error. But if your data set is bigger, then using this rule of thumb of k is equal to the square root of n divided by 2 is a good estimate to start your analysis with. Let's take a look at an example of classifying categorical outcomes with the KNN algorithm and what the steps look like if we run the algorithm in Excel manually, step by step. So I'm going to switch my screen to the Excel where the example is. To illustrate this classification use or classification application of KNN, suppose that there is a training set which consists of 10 observations that you see on your screen in front of you. For this example, we will refer to an observation with the loan default value of 1 as a person who has a high probability of defaulting on their loan, and a loan default value of 0 as a person who does not have a high probability of defaulting on their loan. So a typical application of this example could be when a new customer comes into the bank and opens up an application for a loan, then the bank system can check what their average balance has been on their checking account and what the age of the customer is to help them identify if this person is potentially going to default on their loan payment or not. So in this case, average balance and age are the two input features which we are using to help us predict the class of this new observation or this new customer. This y variable in this case is categorical because it has 0, 1 values only, and it's also binary. So you could have multiple output values for categorical variables. It doesn't have to be limited to 2, but just for this simple example, we'll use a binary categorical variable, and we will use two input features, average balance and age, which will help us identify or predict the class of a new observation. So in our training set, we already have 10 observations that we know the value of the input features for them, and we also know their class. So out of these 10 customers that the bank already has, 5 of them are likely to default on their loan payment, and 5 of them are unlikely to default on their loan payment. Then comes in a new customer who has an average balance of 900, and the age of this new customer is 28 years old, but we are unsure about the class of this customer. So we're not sure if the person should be in class 1 or class 0. So we're going to use the KNN methodology to help us predict the class for this new customer. So let's begin our analysis. In order to start with the analysis, the algorithm says that you have to identify the input features first. In this case, we have already identified 2 input features which we are going to use to help us predict the class of this new observation. The second step is to identify the measure of distance that you would be using. Now, like I said earlier, there are multiple measures of distance available for you to use, but we're going to stick to the Euclidean distance. Now, before we start calculating the distance of this new observation from from the other observations in our training set, a good practice is to normalize your input variable values. The reason why we normalize input variable values is because, as you can see here, the first input feature is average balance, which is in dollars, and then you have age, which is in years. Both of them have different units of measurement, and therefore the scales of these two variables are quite different. Age would be between, let's say, 20 years old all the way to 80 years old, whereas average balance could be anywhere from 0 or even negative balance all the way to $1 million, $10 million, and so on. So because of this difference between the scale in your input variables, a good practice is to normalize these values just so that we can bring them to the same scale level, and that way calculating the distance would be safer because we're not introducing any sort of bias due to the different units of measurements used in the different input features. So in order to calculate the normalized values of both average balance and age, we first calculate the z-score for both average balance and age. Normalization, or calculating the z-score, or sometimes it's even referred to as standardization, can be done using this formula that I've added to the screen here. Z-score for any variable x is calculated as the value of x minus the average of x divided by the standard deviation of x. So let's tackle average balance first, and according to the formula, we would need the average of the average balance and the standard deviation of the average balance. So let's calculate that here first. I'm simply going to use the average function in Excel to do that. Notice that when I'm calculating the average balance, I'm only using the training set and I'm not using this new data observation, which we have to classify. So the average balance in our training set of 10 observations is $1,285. And the standard deviation, again, I'm going to use the simple Excel standard deviation formula, and I'll use the sample one because this is clearly a sample and not a population. So again, I'm only calculating the standard deviation without this new data observation in it. So now you know the average and the standard deviation of input feature number 1. So let's calculate the normalized values for average balance. And according to the formula of the z-score, you would have to subtract each average balance from its mean and divide it by its standard deviation to get the z-score associated for each observation. So for observation number 1, the z-score would be 49 minus the average of 1285 divided by the standard deviation of 2029. And since the average and standard deviation remain constant throughout, I'm going to type this formula in such a way that I can simply drag it down to calculate the normalized average balance for the remaining 9 observations. And to do that, I'll make these references, these cell references, absolute by pressing F4. And this way, Excel adds these dollar signs to these cell references to keep them constant when we copy this formula elsewhere. So for the first observation, since the observation value is below the mean, you see that the normalized average balance is negative, and that's okay. We can have normalized average balances negative, or normalized input features in general have negative values when they are below the mean of that input feature. So now I can simply drag this down to populate the normalized average balance for the remaining 9 observations in my training set. And I can even calculate the normalized average balance for this new observation as well. So I'll drag it down one more cell, and since this new observation 900 is below the average, the normalized value or the z-score for this observation is also negative. So the next step is to normalize our next input feature, which is age. Again, I would have to first calculate the average for age and the standard deviation for age to get the z-scores for each of these 10 plus 1 observations. So what I can do is simply copy this average formula across to get the average age, and copy this standard deviation across to get the standard deviation for my next input feature, which is age. So here again, I'm going to apply the z-score formula, but for this part, we're going to use column C instead of column B because these are normalized values of age. So the first step is to find the difference of each observation from its mean, and then divide it by its standard deviation. And since mean and standard deviation remain constant, I'm going to put absolute cell references. You can type out these dollar signs manually or just press F4 on your computers when you put your cursor in between these cell references to automatically add these dollar signs. Once I do that, I can drag this down to get the values of the normalized age for the 10 observations in my training set, as well as my new data observation for which the class is still unknown. And again, since the age of this new customer is below our average age, you'll see that the normalized age or the z-score for this customer is also negative, which is okay. It's completely fine. Okay, so now that we have normalized both our input features, which we are using to help us predict the class of this new observation, we are ready to calculate the distance of this new observation from the observations in our training set. Now, because we're using the Euclidean distance, it would be useful to have the Euclidean distance formula here. So let me bring that formula in here. I've brought the Euclidean distance formula for reference here if you want to refer to that. But basically, in order to calculate the Euclidean distance for two input features, we would have to find out how far away this new observation is from each of these existing observations in our data set. So we're going to subtract or find the difference between this normalized new observation and each of these observations in our training set for each feature. So first we're taking the average balance. We subtracted the normalized average balance of this new customer from the normalized average balance of customer number 1 and square up this difference and add the squared up difference of the next feature to it. So now feature number 2, the normalized age of this new customer minus the normalized age of customer number 1. Again, square up this difference, and this whole sum needs to be taken the square root of. Make sure that you're using the correct number of parentheses here. If you start a parentheses, you should have an accompanying parentheses to close it, so it always should be in pairs. So basically what I did was got the difference of this new customer's average balance from the customer number 1's average balance and added that to the difference of this new customer's age from the age of customer number 1. Here I'm trying to calculate the distance between this new customer and customer number 1, which already exists in our training set. So again, because this new customer's values would remain the same, what I can do is I can create absolute cell references for this new customer's values, and that way I can simply drag this down to get the distance of the new customer from the 10 existing observations in my training set. So now I know the distance between this new customer and customer number 1, which is 1.068. So I can simply drag this down all the way. And you can see that I had to calculate the distance between the new customer and the existing 10 customers, but I dragged it down further just to make sure that my formula is entered correctly, and the distance of this new customer from itself comes out to be 0, which just shows that the formula has been added correctly. This is just a check to make sure that my formula is working correctly and I didn't make any mistakes while inputting the values. Okay, now that we have the distance of this new customer from the existing 10 customers, most of my work for KNN has already been done. Now, in order to make things easier for myself and just to see which of these 10 customers are the closest to my new customer in terms of the distance that we calculated here, what I can do is I can simply copy this whole thing and then filter it or sort it by distance. So let me get rid of these two formulas here and make a copy of these columns just so that I don't mess with these existing values when I sort and filter. Okay, so all I did was that I removed the reference formulas that I had up here and made a copy of the columns above down here, just so that if I'm sorting and filtering out, I know that this was my original data set values. And one additional precautionary step that I'll probably take, which is a good idea in this case, is that I'll paste these values as only values and not as formulas, so that if I move things around, these numbers do not change. Again, this is not a necessary step, but I'm just doing it to be cautious so that I don't make any mistakes while I'm explaining this example to you. So now what I'll do is I will filter based on distance, and I'll filter from smallest to largest. And obviously, when I filter from smallest to largest, the newer observation of average balance 900 and age 28, let's highlight this for easy identification, is closest to itself, obviously. And the next closest observation to this new customer is customer number 2, which has a distance of 0.2, the smallest distance. So the nearest neighbor to this customer is customer number 2. Let's call this customer number X. So for customer number X, the nearest neighbor is customer 2, the second nearest neighbor is customer 6, the third nearest customer is customer number 7, and so on. So now basically I can test my algorithm with different values of K to see what the predicted class of this new customer X is going to be. Let's note down the predicted class for our new customer X for different values of K. Since I have 10 observations in my training set, K can either be 1, 2, 3, all the way till 10. And the predicted class for our new observation X, would depend on this value of K. So if we select as K is equals to 1, then the predicted class of X is what the nearest neighbor's class is. The nearest neighbor is customer number 2, which has a class of 1. So based on k is equals to 1, the predicted class for x would also be 1, which is the same as customer number 2. If k is equals to 2, if we set k is equals to 2, then we're using the two nearest neighbor values to help us predict the class for x. And because these two neighbors can have different classes, we have to average it out. So since neighbor number 1 has a class of 1 and neighbor number 2 has a class of 0, the predicted class for x would be the average of these two, and that's 0.5. And this is where the cutoff value matters. So generally the cutoff value is set to 0.5. If cutoff is greater than 0.5, the class is assigned to 1, and if the cutoff is below 0.5, the class is assigned to class 0. In this case, since it's exactly at 0.5, we can safely say that this should be assigned a class of 1. Then let's move on to k is equals to 3. For k is equals to 3, we are using the three nearest neighbors to help us predict the class for x. Now, the three nearest neighbors are customer 2, 6, and 7, and the average for these three class values would come out to 1 plus 0 plus 0 divided by 3. Now this value is below our cutoff value, so that means the predicted class for x based on its three nearest neighbors is 0 because it's less than our cutoff value. The same way for 4 nearest neighbors, you can see that the first one has a class value of 1 and the next 3 have class values of 0. So the average of those would just be 1 divided by 4, which is again less than our cutoff value, so the class assignment would just be 0. And I'm doing this manually, but basically if you run this algorithm in other software like R or Jump Pro, they do this part for you automatically. So you don't have to worry about doing it, but this is useful in understanding how the algorithm assigns the predicted class for new observation. And similarly, you can continue doing this for k is equals to 5, for k is equals to 6, 7, and so on. I have the completed example here in front of me for all the 10 values of k, and if we use our rule of thumb, the square root of n divided by 2, the optimal value for k comes out to be approximately 2. So based on k is equals to 2, the predicted class of this new observation x is 1. And if you look at the chart over here, where on the y-axis you have the normalized age, on the x-axis you have the normalized balance, this new observation is closest to this observation here and the other observations which are slightly farther away from it. So based on the k value of 2, the predicted class for this new observation is 1, which means that the bank can assume or can say that based on our analysis and our historical data, a customer with an average balance of 900 and age 28 is probably going to default on their loan payment. In the Excel example that you just saw, we helped classify a new categorical outcome with the help of the k nearest neighbor, and we said that the most optimal value for k was 2. At this point, it's still naive to say that that is the most optimal value of k because we haven't really calculated any classification errors yet, since we have not covered performance measures at this point. So we're just using this rule of thumb to get the optimal value of k. But once we've covered the topic on performance measures, it would be more clear as to how we can select the most optimal value of k which is referred to as K star. So now let's take a look at another example where we are going to use the example to help us estimate the continuous outcomes with K nearest neighbor. In the previous example, we were classifying the outcomes, but here we want a quantitative number as our value, not a categorical value. So for this example, this is a very simple example. We're just only going to use one input variable just so that we can demonstrate how KNN can be used to estimate quantitative values, and this estimate can be used to replace missing values in your data set if there are any. Again, similar to the categorical outcomes example, the value of K could be 1, or it could be from 1 all the way till n. If K is set to n, which is the full sample size in your training set, then the new observation's outcome value is estimated by the average outcome value over the entire training set. Too small of a value for K results in predictions that are overfit to the noise in the training set, whereas too large of the values of K result in underfitting and it fails to capture the relationship between the features and the outcome variable. So let's switch my screen to the Excel example for estimating continuous outcomes with K nearest neighbor. In the previous example, we helped classify the lone default variable with the help of two input features, which were average balance and age. Now, in this example, I'm using the values from the same example as earlier. The only thing different here is that instead of classifying the lone default outcome, I want to find out what the average balance of a new customer will be if I already know their age. So in this case, I'm only using one input feature to help me get the average balance or predict the average balance. Now, because there's only one input feature, there is no scare of having multiple scales or multiple units of measurement. So in this case, normalization is not necessary. We can simply move on to calculating the distance. And because there's only one variable that we need to calculate the distance, so it's just age minus the age. So we don't have to use a fancy formula here. It would just be the difference of this new observation from each of these existing customers. So customer number 1 is 1 year older than our new customer. The same way, if I just simply make the cell reference for this new customer constant, I can drag this formula down and you'll see how far away each observation is from our new customer X. So here I did not use a fancy formula to calculate distance because it's just one input variable. You can do that with one input variable. There is no need for standardization or using a Euclidean distance or Manhattan distance or any of the other distance measures. You can just calculate the differences to get the distance as to how far this new observation is from our existing observations. But one additional step that I'd like to take here is I want to calculate the absolute value of this distance, because it doesn't matter if my neighbors are older or younger. I'm just interested in the absolute value of this distance. So I can use the ABS function, which calculates the absolute. It basically drops the negative sign. That way I can get the measure of distance without the sign being involved in here. Now, because I had already done this example on my own and sorted it out, you'll see that the distance has already been sorted out based on the smallest distance first. So based on age, observation number 6 is the nearest to our new observation X, then observation number 2, and so on. Now let's get the value of K. K can range anywhere from 1 to 10. and we're going to predict the average balance based on each value of k. So if we use k is equals to 1, then the closest neighbor to x is observation number 6. So the predicted average balance of customer x is going to be what the average balance of customer 6 is, which is equal to 36. If we use k is equals to 2, the two closest neighbors to customer x are actually, there are three closest neighbors because the average distance of x from 2 and 10 are the same. So k is equals to 2 essentially becomes k is equals to 3. So these three neighbors are customer 6, 2, and 10, and their average balances are 36, 671, and 2100. So the predicted average balance for our customer x would be the average of these three nearest neighbors. And similarly, for k is equals to 3, this value is going to remain the same. So there is no difference between the predicted average balance when k is equals to 2 and k is equals to 3. For k is equals to 4, the average would be the average balance of the four nearest neighbors, which are customers 6, 2, 10, and 7. So based on this type of assumption and what we're doing here, you can continue doing these steps and get the predicted average balance for each value of k. Here I have the completed analysis for each value of k from 1 to 10, and notice that the average balance for our full training set was 1285, and the predicted average balance for this new customer, if k is equals to 10, comes out the same as the average balance of the whole training set, which is a rather naive way of assigning or predicting new values for new observations. But obviously, depending on what classification error values you get for each of these, you can select the most optimal value of k. At this point, since we have not covered performance measures yet, you can still use the under root n divided by 2 to get the most optimal value of k, which comes out to be 2. So the predicted average balance for this new customer, the age of 28, comes out to be 935. I hope with the help of these two examples, the KNN methodology was clear to you and how different software algorithms apply this KNN methodology to help us either classify unknown outcomes or get the quantitative values of different variables in our data set which are needed. The KNN has its own advantages and disadvantages. The advantages include that the algorithm is simple and easy to implement. There is no need to build a model, tune several parameters, or make additional assumptions. You can just calculate the distance and based on the distance, get the predicted values. The algorithm is also versatile and it can be used for classification, regression, replacing missing values, or searching. However, the main disadvantage of KNN is that it becomes significantly slower as the volume of data increases, which makes it an impractical choice in environments where predictions need to be made rapidly, which is why you'll read in a lot of places that KNN is in fact a lazy learner. Moreover, there are faster algorithms that can be used to produce more accurate classification and regression results compared to the KNN. However, provided that we have sufficient computing resources to speedily handle the data that you're using to make predictions, KNN can still be useful in solving problems that have solutions that depend on identifying similar objects. As an example of using KNN algorithm is in recommendation systems. So for example, Amazon, recommending products on Amazon, recommending articles on Medium, or movies on Netflix, and videos on YouTube. For all of these applications, KNN can be used.